Thanks. Hi, everybody. It's so nice to be here. I've really enjoyed all the talks today. I have learned so much from everybody. So thanks again. And I just wanted to say, I think our talk is going to be under 30 minutes. I'm not sure, but I timed it, and I think it's a little bit less than 30. So maybe we won't be so late. Okay, so we've already been introduced, so I don't need to go through the title slide again. But I want to start with an acknowledgement slide. Usually this goes at the end of a presentation, but I find that as a result it's quite rushed, at least when I'm giving presentations. So I first want to start by thanking ACT Autism Community Training for their partnership. They are helping us engage with stakeholders through events like this and to recruit participants for our studies. I also want to acknowledge our many co-investigators and collaborators, some of whom are here today. Nicole should be on the list. This is an old version of the slide that somehow got plopped in. And some of these individuals are from academia and some are from the community, so it's a really nice mix. I want to acknowledge our wonderful and talented trainees, otherwise known as highly qualified personnel. They have made incredible contributions to the development of our technology, and we wouldn't be able to be where we are at this stage without their work. Our advisory team, which is made up of family members, experts from the field, and autistic individuals with lived experience. And finally, actually not finally, our funder, the Kids Brain Health Network, they've been supporting our research since 2018, so we're deeply grateful for their support. And I want to also acknowledge the contributions of families and autistic individuals with lived experience for participating in our research. We really need that kind of participation in order to understand this problem of decreased sound tolerance and see how we might be able to help. Okay, so I don't need to define autism. I want to just maybe rename sound sensitivity to decreased sound tolerance. This is sort of a more contemporary term anyways. And this is a really broad term that describes people who show abnormal responses to sound without any corresponding differences in hearing thresholds. And as we just heard from Patrick, it's a very complex issue. It's very common in autism. So there's a recent meta-analysis looking at the prevalence of decreased sound tolerance as a broad category, and it's between 50 and 70%, so it's a very common issue. And we know from our research and that of others that decreased sound tolerance significantly interferes with autistic children's participation in everyday activities and is associated with poor mental health and lower quality of life in adult samples. So this is a really important area, and I'm so happy that we're coming after Patrick's talk because some of the definitions that you're going to see are going to be well known, familiar to you. So when we're thinking about understanding decreased sound tolerance and helping people manage decreased sound tolerance, we're met with at least two problems. First, there are patterns, but there is no one pattern, and I think we've seen that today as well throughout the talks. The second is that in our opinion, and that of the people we've engaged with in the community, current solutions for helping those with decreased sound tolerance have some pretty significant limitations. And I'm going to go through these in this talk. Okay, so the first problem, I'm just going to give you some examples of how there are patterns, but not necessarily one consistent pattern. We already talked about misophonia, but I'll go through sort of the three accepted current definitions of decreased sound tolerance. Hyperacusis, which is the perception of everyday sounds as excessively loud or painful, and these sounds would not bother most people. Misophonia, which as we heard is an excessive and at times inappropriate emotional response to specific trigger sounds, and these are often human produced like chewing, lip smacking, breathing sounds, but they can also be non-human produced. They can be repetitive like clicking, keyboard tapping. And as Patrick mentioned in his previous talk, it's often about the intensity of the reaction as opposed to the amplitude of the sound. So the sounds themselves tend to be quite quiet. And phonophobia, which is another thing we've been talking about today, is a specific fear of sound. So even anticipating a sound might occur elicits a fear response. The tricky thing is that these are not mutually exclusive conditions. They can co-occur in the same individual. And so it's kind of difficult to draw the line between them. And as an example, phonophobia might develop from having hyperacusis. So a fear response could develop from having a sensory reaction to sound that's been painful and distressing in the past. And as I mentioned, this is not related to hearing ability. So this is not like super hearing. This is unrelated to that. This slide is a bit jargled, but that's okay. I'll just walk you through it. Another example of this issue of there being patterns, but not really a consistent one, is that the reactions to sounds vary in the type of reaction and also its intensity. So the most commonly endorsed reactions that parents have given are their child gets stressed, irritable, scared, or nervous. And if you look at behavioral or physical reactions to sound, some of the more common ones are, the most common one is covering ears, but we also have more concerning behaviors. I'm sorry, those colored patches are supposed to line up with self and other injury, okay? So you can see a big range in the severity of the reactions as well. The other thing that we've found that's really interesting, and I think has been highlighted today as well, is that reactions can be context dependent. So a good example of this is from a focus group that we ran with family members, with parents, and one father told us that, well, his daughter is sensitive to the sound of a vacuum cleaner, but if she's using the vacuum, it's not a problem, right? So there is some level of autonomy and control that is important to think about as well. That makes it also tricky to predict what situations will be problematic and which ones will be okay. Yeah, again, sorry, this slide, I didn't realize that there's, so I've got basically percentage of the sample. I'm sorry, I should have walked through you what the slide is. This is basically our sample of survey respondents. And so on the y-axis, you can see the, here I'm pointing wildly with my arms. I could just use the pointer. Is that going to work? Yeah, okay. This is percentage of the sample. Okay, so the nature of the sounds. This is another thing. There are patterns. So the most commonly endorsed features of sounds are loud, sudden, or high-pitched. This is from our survey. But other sounds that don't fall in these categories are also commonly reported, and this is often in sort of we give people a chance to free-form respond, so it may not be in our list of sounds, but we heard things like broom sweeping, clock ticking, a tap running, things like that. And Connor mentioned in her talk, the sound of a microwave beeping, so it doesn't have to be necessarily loud for it to be a problem. So the take-home that we have sort of gathered from our research is that decreased sound tolerance in autism presents with variable reactions, behaviors, and nature of sounds. So I just want to present a few quotes, kind of similar to what Connor's approach was today. I think these are really rich sources of data that kind of do a better job than bar graphs. So here's some caregiver quotes. He says that dogs barking, buzzers, and crowded areas that are loud make his ears hurt and is scary for him. He says it's scary because it surprises him. He says that the sound of sweeping with an outdoor broom hurts his ears and is painful. He says the sounds at a hockey game or in a crowded mall are annoying and make him feel irritated and overloaded. And then relating to attention and filtering and concentration, he has said that when a sound bothers him, he can't concentrate on anything else and it's distracting. Here's another quote. It's a little bit small, but I'll read it. This is really illustrating the impact that decreased sound tolerance has on family activities. My son has had sound sensitivity since he was an infant. It affects everything we do, simple outings to a mall. We have to plan carefully around the washrooms. The flush toilets are very loud. The hand dryers are very loud. We have to make sure that we use the toilet at home first and make sure that wherever we go, whether it's a restaurant or a mall, that we can access a handicapped bathroom. He still needs assistance with toileting, so we make sure that one of us can be there and that we do not run the dryers. I pack paper towels and Kleenex is in my purse to dry his hands, or he can use my sweater to avoid using the hand dryer. So this mother is discussing how the great lengths that she has to go to protect her son from these particular sounds that are quite loud and annoying to him. Here's another example of how decreased sound tolerance can lead to social exclusion. In the school setting, the noise at lunchtime in high school cafeteria prevents my daughter from making social connections. She isolates herself in a hallway. But as EAs do not monitor her at lunchtime, they miss an opportunity to encourage a few students to spend some time with my daughter in another location. Instead, every lunch is spent in solitude. And then at the bottom, completely freaked out. He could hear an ambulance siren at least 3 minutes before anyone else heard it. Very frightened and tearful. We also spoke to autistic adults in our research. So these are individuals who self-reported as having a history of decreased sound tolerance. At current also, as not just a history. So here's a quote. Maybe I won't be able to get through all of them, but I'll read the top and the bottom one. Unable to fully participate in society because so many noises trigger me and so few people are willing to understand and accommodate. Attempts to get accommodation usually results in being bullied and or abused. And then the bottom one we think is really interesting because obviously our work is around developing technology. I avoid going in public places that I know will be too noisy for me, and I have almost been hit by cars because my noise-canceling headphones drown out vehicle sounds, which I also happen to be afraid of. Okay, so I'm not going to go into detail about brain mechanisms. This is also a really small font. What I will say is that we're still trying to determine the mechanisms underlying decreased sound tolerance and to determine if the mechanisms that are operating in autism are somehow different from what's happening in non-autistic individuals. There are some leading hypotheses. I can just list them here for you, but one that's gaining a lot of traction is the idea of increased central auditory gain, which is basically the brain is ramping up auditory information. An excitatory inhibitory imbalance is another related concept, and that seems to be explaining, it's kind of getting a lot of traction as a general explanatory mechanism for some of the differences seen in the autistic brain. Problems with sensory gating, so filtering information. We heard this morning from Kelsey some examples from her practice around filtering information and leading to sensory overload. And then differences in sensory limbic connection. So this could be a learned response or just a difference in the way the brain is connected so that sensory information is more likely to activate parts of the brain that signify threat or relevance. So we don't know which one is the most relevant. Maybe Patrick will have more insights on this coming from UC Davis. But they each have implications for treatment and what we would do to manage and help the individual. And as we've talked about today, there is not widespread agreement on exposure therapy, but it might be effective for some situations and not for others. So it really depends on, I think, what's underlying the problem. But okay, problem 2. Current solutions are limited. So from our research, we found that caregivers most commonly endorse behavioral strategies for helping their child cope with their decreased sound tolerance. So this includes things like avoiding the noisy setting altogether and warning their child of an upcoming sound. And they are effective strategies, but they do have some limitations. So first, if we're avoiding noisy situations, we're being excluded from those activities. And it also relies on the presence of a knowledgeable human to know which areas are safe and whether or not a sound might occur. Wearables, as we've talked about today, are also really common. Everything from ear defenders, earplugs, to advanced noise-canceling headphones. But these also have some limitations, according to the research and our discussions with autistic individuals. So some of them block too much. So this is obviously a safety concern. We just saw a quote. I read it out about the person who was almost hit by cars on multiple occasions. And also there's social exclusion if you're blocking speech, right? So you can't really have a conversation with somebody if you can't hear what they're saying. or they may not block enough, right? So they might block quite a bit, but then the very sound that you're aversive to still gets in and can cause a reaction. And we've heard that from our participants as well. And none are really flexible. Like, I think people are doing a lot of swapping between devices to kind of suit the need of the environment that they're in, and that's fine if that works for them, but it might be nice to think about something that's more flexible. We asked autistic adults about what solutions they wished existed, and here are some quotes. Understanding in others, no gaslighting, you're too sensitive, ability to tune out triggering sounds, headphones or earmuffs that block background noise but allow a main focus sound to pass through. For example, if a person is talking to me in a busy restaurant, block out all the other sounds except the person's voice. And I'll just scroll to the bottom. The third one I think is really important. Understanding employers that will accommodate for these things. We did speak to some autistic individuals who were forced to kind of take off their helpful ear defenders because they were in an environment where it wasn't acceptable according to the employer. And then the last one is earplugs that canceled noise but allowed me to hear what I need to hear. And accessibility was another one. Obviously, cost is a major issue. Okay, so there are lots of examples. I need to move on. I could read quotes all day. Overarching goals and expected impacts. So what are we doing in this project? Our goal is to develop and test new solutions that are better suited to the unique problem of decreased sound tolerance in autism. We're working on a smart device that can intelligently detect and filter aversive sounds that are specific to the end user. Our goal is to increase participation in social, educational, and recreational settings, which we hope will improve quality of life and lead to better educational and social outcomes. So I'm going to pass you over to Siamak now.
Thanks, Elina. I want to use the moment to introduce the device. So the device that we are building is composed of a headphone with reasonable sound isolation. It has a built-in microphone that captures the environment's sound. It also has a small microprocessor that processes the sound and stream it back to the user. The processing part has two components, detection and management. For both of these two units, we use artificial intelligence. For the detection part, it identifies the occurrence of the aversive sound in the environment. Currently, we are detecting 5 sounds: siren, dog barking, baby crying, car horn, and jackhammer, and we do it with a very high accuracy. When the aversive sound is detected, the management part starts, and the management part basically includes different options. We can stop streaming the signal. We can reduce the volume. We can also selectively remove the aversive component of the sound and play the clean signal. And we can mask the sound by playing music or white noise. In the next slides, I'm going to show you a demo of how the filtration part, the part that we remove the aversive component of the sound, works. The device also has some additional features. It gets better as it is used, so it has the learning capability. It is fully customizable. The users can adjust the device based on their needs. And following the question that was asked in the first part of the today's Q&A, this device can be adjusted to let the users to gradually expose themselves to the aversive sound if they want to. And this is a very good feature that we think is going to help the users to increase their tolerance. And for some of the important signals that we are removing from the original sound, we provide alert. For example, for siren, although we can remove it, we can provide a signal to the user that it was the siren that is removed from the whole sound. I already explained the device, how it works. It has headphone and it has a microprocessor for processing the sound. We also have a user interface, and with this user interface, users can select different options. For example, they can select what aversive sounds they want the device to manage. They can also upload their preferred music for masking, and different preferences they can select, and the device is going to act accordingly. I already told you that the detection part and the management part benefit from the AI in their operation. Probably you heard about the advancement of AI in image processing. Other applications like ours are trying to piggyback from the advancement of technology in that area. Just to briefly explain for you how it works, the AI engine receives maybe millions of labeled pictures, and then the training starts. After the training gets to an acceptable percentage of accuracy, the AI engine can now detect any unseen picture. And that is how it works, in a very brief explanation of the complex AI work. In our application, we converted sounds to pictures using spectrograms. So I try to use the pointer here. You can actually see different pictures that are created from various sounds, and you see the differences between them, and that is how the AI system identifies different sounds. If you remember, I explained we need millions of these pictures for training the AI algorithm, and we didn't have access to a large library. So what we did was, again, using AI to create some fake images that are not distinguishable from the original ones. Probably you remember the Obama fake video. It is exactly like that. And using these fake images, we improved the accuracy of the device significantly. And for the filtration, today you heard about noise-canceling headphones. So those noise-canceling headphones, the main processing is digital signal processing, and this technique is very good when you have the range of frequency of the noise, for example, the engine or the air conditioner. But for complex signals, noise canceling is not going to be very effective. So we needed to come up with a different technique to be able to handle these complex situations. And that is where we used AI again to selectively remove the aversive components of the sound. And I want to show you a demo of how the filtration works.
In this video, I will show you the demo of the software. On the right side, you can see the first page of the software. The software is currently running on AWS EC2 G3 instance using Wi-Fi, and it is connected to my local microphone and headset through API. The microphone is streaming all the sounds in my surroundings, including my voice and any other noises, but this speaker is playing the sounds that come out of the software. So what you hear now is the output of the system, which is exactly playing into my ears. Since there is no aversive sound in the environment, the classifier says it is a normal status and the filtration is not activated. But now I will play an aversive sound, a siren sound, to see how the system works. We expect that the system detects the aversive sound in a few seconds and show the status bar as an aversive sound and then filter the sound. So let's see. As you can see, the system detects siren as an aversive sound and it's changed the status bar to aversive sound to show the user that there is aversive sound in the environment, and it is filtering it right now. You can hear my voice clearly, but there is no siren in it. For now, I will show you that there is an aversive sound still in the environment. I will turn off the filtration manually, so you can hear siren again, and there is a siren. I will turn on again the filtration, and now the system is filtering it, and you cannot hear the siren. I will turn off the sounds, and then the status of the system will be back to normal. Means that there is no aversive sound in the environment. I will try another sound, a dog barking sound, to see how it works. You can see the system detects aversive sound again, and it's changed the status bar, and now it's filtering the dog barking. You can hear my voice again, but there is no dog barking in the sound. I will again turn off the filtration to show that there is a dog barking here. You can hear dog barking. The system is not filtering it, and then again I will turn it on. And now you cannot again hear dog barking. It's filtering it. I will turn off the dog barking sound, and the status of the system will be back to normal. As you saw, the system is able to detect the aversive sound in a few seconds in the environment, and then change the status bar to aversive sound, and then filter it immediately. Thank you for watching.
Okay, now I hand into Elina again.
Okay, so we're still, of course, working on it, making improvements, but we have tested one version of the system with autistic adults in a controlled setting. And so just so I can walk you through this table. So what we did is we gave participants a comfort rating. They had to give us a rating from 1 to 4. 1 is very comfortable, 4 is very uncomfortable. So higher numbers is bad. And so we presented different conditions. So the top one where you see baseline, if you can see that. Baseline means nothing was changed. It was just streaming through. The second one was siren with music playing as a masking sound. The third one was white noise over top of siren. And then we had our filtration kick in as a third condition or fourth condition. Siren with filter without speech. So we had two conditions there. One where there was a speech sound happening. And so as you saw in that demo, it was filtering out the siren, but the speech was still there. Sorry, that's the fifth condition. The fourth condition is there was no speech at all. And we did this exact same thing for dog barking. And so what we found is that relative to baseline, where there was no intervention at all of the conditions produced some benefit relative to baseline. The most improvement was found for filtration without speech. And part of this was because this was an older kind of version of the algorithm. So the filtration with speech was not producing very high speech quality, but we've made improvements since then. So we're really excited to test that in the lab. So filtration without speech seemed to produce the most improvements, particularly for dog barking, where it seemed to work the best, at least in that version. Okay, so hoping that makes sense. If you have any questions about this table, I know it's kind of busy, lots of numbers in there. Okay, so one participant's feedback, I wasn't able to put everyone's in, seemed to work very well. It's the same as noise-canceling headphones with sound. It was good. I prefer the filtering over music or white noise. Still able to hear what is going on around me. When I listen to music or white noise, I'm cut off from all sound, which in some situations could be problematic. I could not hear the dog barking at all, other than through the external laptop speaker. Okay, so we're getting near the end here. Current and next steps. So just put a little plug in for a study we are about to launch, testing the performance and user acceptability of the system in a VR setting. And we're doing this because we want to better approximate how sound and stimuli are experienced in the real world without throwing people out in the real world, which is very, very chaotic and uncontrolled. So it's sort of a first step towards a field test. So we will be seeking participants. I'll let you know when this study is ready to advertise. Right now we're focusing on youth and adults, youth aged 12 and up. And of course we offer compensation for participation. We'll also be this year and also into next year doing a small field test in community settings, possibly classroom as well. Again, with youth and adults, community settings, so that's a lot of overlap there with what I just said, and then a $100 honorarium as a compensation. And this research is being done in partnership with ACT. So I just want to show you a couple of examples of the VR environment that we've programmed. So we have a neighborhood scene on the left, and we have a city scene on the right. And on the bottom, you can see some examples of stimuli that are typically associated with sounds that are problematic for people on the spectrum. So construction workers, an ambulance, and a dog. So we can talk more about that study if you want at the Q&A. But I just wanted to end by thanking again the families and autistic individuals who have given us feedback so far on our idea. And this has been through focus groups, through interviews, from the very earliest stages, and of course in the lab as well. So, and once again, thanks to our funders. Thank you.
Thank you. I first learned about this in 2018, and I think, you know, like a lot of initiatives, the pandemic had a huge impact. Things stalled for a little bit of time, but it's so exciting to see, you know, your slides of the actual product and what this will look like, because it's exactly what I envisioned, and to see it there is amazing. So thank you. The last question was from Tiffany, and the first question today for this session now was from Tiffany as well. So she was having a little bit of challenge streaming, which we're hoping she won't have tomorrow. But she says, I may have missed this because my signal cut out for a bit, but did you say that this technology can presently filter chewing and other common misophonic triggers, mouth, nose, throat sounds with high accuracy?
Not yet. It has the capability to learn that, but right now it can detect those sounds with very high accuracy. We have a paper that we're presenting at a conference in July, an IEEE conference, that shows the detection piece is there. So we're working on the filtration part for those mesophonic triggers, yeah.
Cool, thanks. Another question. Can this same filtering be used to increase the intelligibility of speech for hearing aid users?
In my opinion, there is no limitation for that. So we can definitely train the algorithms and use it in a different way. So I think what we do can cover that as well.
Oh, thanks. Another question related to detecting quieter triggers, but from your last response, I'm guessing, you know, whatever we can think of as a possibility. So that's very exciting. Any other questions from the group here?
You guys have been so great paying attention to our talk at the very end.
The last question from Sarah relates to, and this has been said a couple of times, Connor mentioned it, or Connor, it might have been Nicole, somebody mentioned amping up versus amping down. And the question relates to, I guess, the connection between that amping up, and is that a purely autistic piece, or could there be some other trauma, such as a concussion, that might lead to that?
Are you talking about the central gain idea that I was mentioning? Yeah, no, that's a general proposed account for hyperacusis, not just specific to autism, but So people like Zach Williams in Tiffany's lab are trying to apply some of those established accounts to autism to see if they hold up. But the evidence is so new, like we're still doing so much research in this realm that it's unclear if multiple things are happening at the same time, if the mechanisms are similar between neurotypical and autistic populations, or if it's just more complex. So yeah, I am not sure about brain injury patients, but definitely people with some aspects of hearing loss. Well, you also have things like loudness recruitment, which ramps up sort of moderate frequency sounds. So I think it's more of a general hypothesis rather than an autism specific one. Yeah.